You're probably wrong about zero gravity. And you're not alone. Most of us have this image burned into our minds. An astronaut floating peacefully inside a spacecraft, totally weightless because they've left Earth's gravity miles behind. Well, that image is a lie. It's one of the most popular myths about space, but it's not the only one. What if I told you that your body wouldn't actually explode if you were exposed to the vacuum of space? Or that going to space literally makes you taller? We're about to demolish what you think you know about leaving Earth. By the end of this, you'll get the beautiful, terrifying, and completely counterintuitive reality of what it's really like up there. Let's tackle the biggest lie of them all, the idea of zero gravity. When you see astronauts floating around on the International Space Station, they are not free from gravity. Not even a little bit. The ISS orbits at an altitude of about 250 miles, or 400 kilometers. At that height, Earth's gravity is still about 90% as strong as it is right here on the surface. So, if an astronaut who weighs 180 pounds on Earth could somehow stand on a scale up there, they'd still weigh around 162 pounds. So, why are they floating? The answer isn't a lack of gravity, but something way more elegant. They are in a constant state of free fall. Think about a fast elevator when the cable snaps. For that terrifying moment, you'd feel weightless as you, and everything in the elevator, fall at the exact same rate. Now, just imagine that elevator is the International Space Station. The ISS, the astronauts inside, and the camera filming them are all falling towards Earth together. But if they're always falling, why don't they ever hit the ground? This is where the magic of an orbit comes in. The ISS is also moving sideways at a blistering 17,500 miles per hour, or about 28,000 kilometers per hour. At that insane velocity, as it falls downwards, the Earth's surface curves away beneath it at the exact same rate. So it's perpetually falling around the Earth, constantly missing the ground. Douglas Adams, in The Hitchhiker's Guide to the Galaxy, brilliantly described flying as throwing yourself at the ground and missing. That's not just a clever line, it's a perfect description of an orbit. That feeling of weightlessness, which is properly called microgravity, isn't from being far from Earth. It's the experience of having no ground or any other force pushing back against you. Here on Earth, you feel your weight because the ground is always pushing up on your feet, fighting gravity. In orbit, nothing is pushing back. You, the station, and everything around you are just on the same never-ending roller coaster drop, which creates the illusion that gravity has vanished. It's a beautiful, continuous plunge that you never land. Okay, let's pivot from the elegant physics of orbit to something a little more messy. Science fiction has given us some truly unforgettable death scenes in space. A helmet cracks, a suit fails, and boom, the unprotected astronaut instantly bloats up and explodes like a gory water balloon. It's dramatic, it's horrifying, and it's totally wrong. You wouldn't explode. Your skin and connective tissues are way too tough. They'd hold your body together against the vacuum. So, what would really happen? It's not pleasant, but it's a lot weirder than you think. The first and most immediate problem is the lack of air. The vacuum of space would rip the air from your lungs almost instantly. After about 9 to 12 seconds, deoxygenated blood would reach your brain and you'd lose consciousness. But in those few seconds before you pass out, you'd experience something truly bizarre. The low pressure would cause the fluids on the surfaces of your body, like the saliva on your tongue and the moisture in your eyes, to boil. This isn't because of heat. Space is brutally cold. It's because the boiling point of a liquid plummets as pressure drops. In a vacuum, your own body heat is more than enough to make your exposed fluids bubble. There's even a first-hand account of this from a 1966 vacuum chamber accident where a test subject's suit failed. He said the very last thing he remembered before blacking out was feeling the saliva on his tongue start to boil. Your body would also swell up. The water inside your tissues would start turning to gas, a process called ebulism, causing you to puff up to maybe twice your normal size. But again, your skin is elastic enough to keep you from popping. You also wouldn't freeze instantly. A vacuum is a terrible conductor, so your body would lose heat very, very slowly. Ultimately, the cause of death would be simple asphyxiation, a lack of oxygen. It's a grim scenario for sure, but a far cry from the explosive endings we see in movies. Death in a vacuum is silent, swift, and strange, but not explosive. Now for a myth that's actually grounded in a surprising truth. The idea that space changes your height. In microgravity, astronauts can temporarily grow up to 2 inches taller. On Earth, gravity is constantly compressing your spine. The gel-like discs between your vertebrae get squeezed all day long, which is why you're a tiny bit shorter in the evening than you are when you first wake up. In space, without that constant downward pressure, the spine just relaxes and elongates. The vertebrae spread apart, letting the spinal discs expand. This can lead to a height increase of up to 3%. Of course, this cosmic growth spurt is temporary. As soon as an astronaut gets back to Earth, gravity goes right back to work, and they shrink back to their normal height, usually within a few days or months. But it's not just height that changes. Living in microgravity is a huge shock to the human body, which is fine-tuned for Earth's gravity. Without the need to fight gravity, muscles start to waste away, especially in the legs and back. Astronauts can lose up to 20% of their muscle mass in as little as 5 to 11 days if they don't exercise like their lives depend on it. Bone density also takes a nosedive. Astronauts can lose bone mass at a terrifying rate of 1 to 1.5% every month, which is similar to the rate seen in severe osteoporosis on Earth. To fight this, astronauts on the ISS have to exercise for about 2 hours every single day, using special treadmills and resistance machines to simulate weight-bearing exercise. Fluids in the body also shift upwards since gravity isn't there to pull everything down. This gives astronauts a puffy moon face and sinus congestion, and can even put pressure on the optic nerve, causing vision problems. Living in space is a constant war against your own body's attempts to adapt to a new and ultimately hostile environment. We're about to bust a few more quick-fire myths, but first, a question. Is your mind a little blown? If you're enjoying having your idea of space turned completely upside down, do me a solid and hit that subscribe button. We tackle the most mind-bending questions about our universe every week, and you won't want to miss what's coming up. Now that we've handled the big ones, let's rapid fire through a few more common space lies. First, the Great Wall of China is not visible from space with the naked eye. This myth has been around for centuries, way before we even went to space. While the wall is incredibly long, it's also very narrow, and its color blends right in with the surrounding landscape. Astronauts, including China's very first astronaut, Yang Liwei, have all confirmed they couldn't see it without a serious zoom lens. You can, however, easily see things like city lights at night, massive airports, and major highways. Next up, the asteroid belt. Movies like The Empire Strikes Back show it as a chaotic, dense field of tumbling rocks that only a hotshot pilot could navigate. The reality? It's mostly just empty space. If you crammed all the asteroids in the main belt together, they'd have a total mass of only about 4% of our moon. The average distance between individual asteroids is around 600,000 miles, or nearly 1 million kilometers. A spacecraft flying through the asteroid belt has a practically zero chance of hitting anything by accident. You actually have to aim very, very carefully just to get close to one. Finally, how about nuking an asteroid to save Earth? It's a blockbuster movie staple. While a nuke is our most powerful tool, just blowing an asteroid to bits might turn one big problem into hundreds of smaller radioactive problems that still rain down on us. A much smarter strategy is to detonate a nuke near the asteroid, not on it. The intense radiation would instantly vaporize part of the asteroid's surface, creating a jet of gas that acts like a rocket thruster, nudging the rock onto a safer path without shattering it. It's less about destruction and more about a gentle but extremely powerful push. From the constant fall we call orbit to the shocking emptiness of the asteroid belt, the reality of space is often way stranger and more fascinating than the stories we tell about it. That romantic image of a peaceful, weightless existence is an illusion. The truth is a story of mind-boggling physics, the human body's incredible and sometimes dangerous ability to adapt, and the sheer challenge of surviving in a place we were never meant to be. Gravity isn't gone. It's the very thing holding you in that perpetual fall. Your body doesn't explode. It succumbs to the silent, cold realities of a vacuum. And saving the world isn't about brute force, but about clever physics. Knowing this stuff doesn't just make for good trivia, it gives you a deeper appreciation for the genius of space exploration and the raw, unforgiving, and beautiful laws that run our universe. So, I'll leave you with a question. What's the biggest space myth you used to believe? Let me know in the comments below. Thanks for watching.